So there's some periodic trends. These are trends, there are exceptions to them, but it can be helpful to have a general idea of these things. So atomic size, how big is the atom? One way to think of this is the distance between the outermost electrons and the nucleus, essentially the radius. What we see is as we go across a period from left to right on the periodic table, atomic size decreases. Okay, this does not make a lot of sense because the atoms are getting heavier. We're adding protons and electrons as we go across, and yet the atoms are getting smaller. And this has to do with the number of protons on the nucleus and the pull of that on the electrons. I need a periodic, there's my periodic table. We'll go back to that other slide. So as we go across in a given row, we see that lithium is larger than neon, and that's not really what you would expect. But what electrons are we adding as we're going across? All of the electrons that we're adding are in the same principal energy shell. They're the same level. So they're roughly the same distance, but we're also adding protons to the nucleus. Lithium has 3 protons in its nucleus. Neon has 10. Positive 10 charge pulls the electrons in closer than a positive 3 charge. The attraction is proportional, oh my, I'm messing this up, Q1, Q2 divided by R. This is Coulomb's law. The force of attraction between charged particles depends on the charges of the particles, and it's divided by the distance between them. So going across here, you're adding electrons at roughly the same distance, but the charge is increasing. The charge on the nucleus is increasing. As the nucleus increases in charge, it pulls the electrons in tighter. As we're going down a column, atomic size increases. This one makes more sense. We really don't have to say too much about it. As you're going down, they get larger. Well, of course they are. You're adding electrons, and you're getting into higher and higher energy levels. You're just putting more layers on the onion. So we should be able to answer questions like this. I'm not going to do all of them because we're running out of time. Choose the larger atom. So PB or PO? Well, you got to find them on the periodic table first. So here's PB, and here's PO. So I'm going to ask you to compare elements in the same row or in the same column. Well, which one's bigger, PB or PO? PB, because as we go across, they get smaller. So lead is a larger atom than polonium. Let's look at rubidium and cesium. So, no, rubidium and sodium. There's sodium, here's rubidium. Which one's bigger? Rubidium. As you go down, they get bigger. Okay? Sometimes they'll give you diagonals, like this one I believe is a diagonal. So they're giving us tin and bismuth. As we're going across, we expect bismuth to be smaller, but as we're going down, we expect bismuth to be larger. We've got the trends conflicting, and I would expect you to say, we can't tell. Sometimes the trends reinforce themselves, like on fluorine and selenium. So here's fluorine, and here's selenium. As we're going across, we expect them to get smaller, so we expect fluorine to be smaller. As we're going down, we expect them to get bigger, so selenium would be bigger again. And so those trends reinforce themselves, so you could predict there that selenium is larger. But this one, you can't tell. Any questions? Ionization energy also follows a trend. The ionization energy is the energy required to remove an electron from an atom. Now we said that, group 1A metals form positive 1 ions by losing an electron, and they want to become like a noble gas. It still requires energy to pull it off. So it's the energy to remove 1 electron. And this follows a trend as well. So removing an electron gives you the noble gas configuration from a group 1A element. If you take an electron from a group 7A element, that doesn't help it, does it? Makes things worse. So this is how I remember it. Fluorine wants to gain an electron. It doesn't want to lose an electron. So fluorine's going to be real unhappy about losing an electron. How about lithium? When lithium loses an electron, it becomes like helium, which is a good thing. So the ionization energies over here are lower than over here. Fluorine's going to fight you pretty hard about taking an electron because he's looking to get an extra. So ionization energy increases as you go across. Increasing as you go down makes sense. Decreasing as you go down. I hate the way they do these arrows. I just have to think through this. So as we're going down, the atoms are getting larger and larger. So the electrons are farther and farther away, and the farther the electron is from the nucleus, the easier it is to pick it off. My very non-PC example is I have 6 children, and because I want to still have 6 children, I don't take them to the big Fresno Fair, because it seems to me that's a great place to lose children, right? So if I took them, I've got 6 children all over the place, right? I can't even hold on to all of them at the same time. And then my friend with 1 child. Who's easier to kidnap a child from? Me. They're all over the place. I don't even know where they are. I can't remember their names, right? Don't turn me in. I still have them all. But the child who's just a single child and his mom is really close, right? It'd be hard to pick him off. So electrons in atoms, small atom, harder to remove an electron. Big atom, all these electrons all over the place, easier to pick one off. So which one has the higher ionization energy? So magnesium, that's not an arrow. Magnesium or strontium? Well, here's magnesium, here's strontium. Yeah, magnesium is going to be the higher ionization energy because this is smaller. Smaller family keeps a better eye on their electrons, right? So higher ionization energy, magnesium. Really, the only way to get these right is to be able to talk this through in your head on an exam. Metallic character. This is actually the easiest one. Okay, so you can read that slide. But here's this line. We learned that this divides the metals and the nonmetals, right? So let's just think about what happens as we go across. So we're going across, we're metals, semi-metals, nonmetals. The trend has been that we go from metals to nonmetals. Metallic character is decreasing, right? It's decreasing so much that we got into nonmetals. So how can a metal be more like a metal than other metals? Well, can a guy be more manly than other men? Gaston, Beauty and the Beast. He's very manly, right? And the same thing is true for women. You could be more feminine or less feminine. Does that mean you're not a man or a woman? No, it's just different degrees, right? So, like scandium is more metallic than cobalt. Metallic character includes things like shininess and conductivity and those sorts of things. And then as we go down, so going down, non-metal, semi-metal, metal. As you're going down, metallic character increases. So that one should be pretty easy. Metallic character, let's pick C. Bromium or tellurium? Well, here's bromium. Bromine. There's tellurium. Come on, tellurium. So how do we think about this? We want the more metallic. Well, even without looking at trends, this is a semi-metal, that's a non-metal. Which one's more metallic? The tellurium. If we're looking at trends, going across becomes more metallic. So we would expect, less metallic. So that would predict that this is less metallic. Going down becomes more metallic, predicting that this is more metallic and that less. That's something you have to talk through your own head. But sometimes you can just tell. Oh, hallelujah.